Welcome back to our channel Easy Peasy Robotics. We explain the robotic concepts to help the community. And today we will understand the TF2-library in ROS, and we will also understand the concepts related to TF2-library such as static transforms, dynamic transforms, frames, how robots use frames to understand the transformations between the components of the system, such as the position of the camera, LiDAR with respect to the robot base, and why the ROS2 and the ROS uses frames as the base to understand the components locations with respect to its robot frame. And before wasting any time, let's directly head towards the video. We will begin with the documentation of the ROS. Open a new terminal and dial ROS humble documentation. Navigate to the documentation, ROS2 documentation. In that, head towards the tutorial intermediate, and here you will see TF2. So this will explain you the TF2 concepts. I recommend going through all of the things, but for now we will be seeing the introduction, how we can create a static broadcaster, and how we can add frames in Python, so as to give you an idea about adding the frames and making your own frames. I recommend going through all of the details to understand the things better. We'll start with the TF2 frames. TF2 is a library provided by ROS which has two components, broadcaster and listener. The broadcaster publishes a relation between the frames that we have created, and the listener will listen to the transformation of these frames and will do further computation. Let us see with an example which is provided by the ROS already. So for that, copy paste this command. I already have that, and copy paste the first command over here, copy and paste, and then run it so as to have the package which will be used in this tutorial. I have this already, so I will not be going through this. Let us start running this demo. So this is a launch file, ROS2 launch, which is used to run the launch files. And now this is the package name, and this is the launch file. The launch file is used to execute multiple nodes at the same time. Let's copy paste this command and let's see. Yeah, now we can see there are two turtles which is also provided in the ROS, and we can see the one turtle is moving towards the another turtle. And let me move this here so that we will see everything. Yes. And now let us drive the another turtle using this command, so which is again a ROS node. This is the package name, and this is the ROS node that will help us to drive one of the turtles. Let's copy, open another terminal, and then paste this command. And now with your arrow keys, you can move one of the turtle over here. As you can see, when I move, I'm moving only the first turtle, and the second turtle is following the first turtle automatically. And the second turtle is a TF2 listener which will listen to the transformation, and now it is following the first turtle. So what's happening behind this? Let's have a better understanding of this. And why we use coordinate frames is a question in ROS. So the coordinate frames will give you the spatial relationship between the objects or frames. Consider we have a point over here, and we know the position of this frame consider this as a world frame, and we can easily find the position of this object in this frame, how far it is along X, how far it is along Y, and how far it is along Z. So like this, we can find the position of the object as well as the orientation of the objects in this frame, and we know the transformation from this frame to another frame which we have over here, maybe as a world frame. Then we can easily find the position of this object in the world frame using this frame. Like this, if we have multiple frames, then we can find the position of this in any of the frame easily. That's why we use coordinate frames in ROS. And in our case, what we have is as follows. We have a world frame, we have turtle 1, and we have turtle 2. And the package uses TF2 broadcaster that publishes the transformation between the turtle 1 and the world frame, and also publishes the transformation of turtle 2 with respect to the world frame. So now, and the turtle 2 and there is a node that uses that has a TF2 listener which listens to these transformations, and it computes the difference between the Turtle1 and Turtle2 using these two transformations. And once it gets the difference, it minimizes this difference by moving towards the Turtle1. That is the reason why the Turtle2 is following the Turtle1, which is based on the frames. And similarly, you can use in practical examples. If consider this Turtle1 is an object, and we know the position of this object in the world frame. And consider Turtle2 is our robot, and we know the position of the robot in the world frame. Then we can easily find the difference using these frames between our robot and the object, and we can move our robot towards the object easily using frames. That's the basic concept of using frames and TF2 library. That's why the TF2 library is really powerful to have these frames and the transformations, which helps the robotic systems to do a lot of things. And TF2 broadcaster has like two transforms, that is static transform and dynamic transform. What are those? Let us see. So this is the robot, and consider this is the robot base, which will move when the robot moves with it. And consider we have a LiDAR over here, or a camera that has one frame over here, and the robot has an arm and it has one frame over here as well. So the static transforms are the transformations that never changes with time. Now the relation between the robot base and the camera is fixed. Since the camera is fixed to the robot, no matter where the robot goes, this relation will remain same, and the transformation between these two frames remains the same. That's why this is represented by static transforms, which continuously publish the same transformations which will not change over time. And when we have the relation between, consider this as a camera and the robot arm, since the robot arm will be moving, the transformation, the relative transformation of the end effector frame and the camera frame will be changing over time as we move the arm. So that's why we have a dynamic transform that give the transformation of the end effector frame relative to the camera or the robot base frame over time. And the time is also really important over here, because it tracks, the TF2 library tracks the relation between the frames over time. So at one point maybe after 5 seconds it might be here, and the relation will give you this, and after 10 seconds the point arm will change, and now we will have at different time we will have that is different transformations, and time also plays a great role in TF2 library. Let's head back to the documentation and move further. With this basic understanding of frames and what is happening behind the scenes of these two frames, the TF2 library also provides the tools which are used to visualize the relation between the frames. Just copy paste this command in your terminal, and then you should see something like this, a tree-like structure that gives you the relation between the frames. When you are working with the big projects, then you will need this tool to analyze how the frames are related to one another. Here it will give you how the world frame is related to Turtle2 and Turtle1. Similarly, there is another, that is TF2 echo, that will print, that will show you the transformation between the frames easily between any frames of over here. We have the relation between this, and you can find the relation between Turtle2 and Turtle1 using this command. So this is ROS2, and from ROS2 TF2 ROS package, this is the node name, and then it will give you the relation of Turtle1 with respect to Turtle2 over here, and it will give you the translation between the frames as well as the rotation between the frames. You can easily use any of the frames that you have available, and you can easily get the transformation between them. And the third one is the RViz, that will help you visualize. It's a visualization. With this you cannot visualize the frames, but with RViz you can visualize the frames easily and what is happening, and you can use RViz for debugging purposes as well. We will see that in the next video, about which will be detailed on RViz and how we can use the visualization tools to visualize the different shapes and all in RViz, how we can use them. Let us copy this command and let's see how RViz can help us. Copy paste this command and you will see interface as this. And if you look closely, there is a world frame over here. If you go, the TF2 will give you this, and if you click on show names, it will show you the names. Now see, there is a world frame over here which is a representation of this, and here is a world frame we have, and we have two turtles over here, and this over here representing our two turtle frames we have. Let us drive the turtle and let's see. When I move the turtle 1, turtle 1 moves and the turtle 2 is fallen. Similarly, we can visualize a lot of things with RViz. As we can see how the two frames are moving, and we can visualize that in RViz. Let's head towards how to create our own static broadcaster and a dynamic broadcaster and how to add the frames. Let us create a static broadcaster that publishes the transformation between two frames, and the relation between the frames never changes, like the robot base and the camera position, and the transformation between them will never change. And to do that, we have seen that writing a TF static broadcaster in Python. Go to this, and I recommend reading all of these commands to understand better how we are doing this. But for now, we will be going for this command, which is the just one command that will give you the transformation, static transformation between two frames. Let us type this command, ROS2 run to run the node, and TF2 is a package, TF2 ROS package, and then static transform publisher. And now it will take the following arguments: x, y, z between the frames, and your pitch and roll, and the frame, the parent frame and the child frame. Let's give as follows. I will give along x1, y0, z0, and pitch, roll, yaw, and roll 0 notations, and I specify world frame as a parent and child as a child frame. Enter. Now it is continuously publishing the difference, the relation between the world and the child frame. Along x it is 1. Now how to visualize this? Open another terminal and type RViz2, which is for visualization of the frames. Now it is showing some issues. We will see why. Add, go to add, scroll down, add TF. So this will give you the transformation. It will show you the frames. Now we can see there is one frame, but here we have an error. And now go to show frames, and we don't have the fixed frame. Will give you the position of the fixed frame. Since we don't have any map frame, click on this, and here we can see there are two frames. We have world and child. Let's go to the world, and here we can see the relation between the world and the child. The red represents the x-axis, and now we have given over here along x it is 1. So now we have along x we have 1. Now the relation between these two is that the child is along x direction and in 1 unit with respect to the world frame. Let's change this relation, and now with x we will also give along y, and you should visualize updated transforms in the RViz. Now we have seen it is along x it is 1, along y it is 1. Let's stop this and again run this with z1 and enter. Now we can see along x it is 1 unit, along y it is 1, and along z it is. Similarly, you can have like multiple static transforms, but it is unlikely that you will be using every terminal for that. And to avoid that, you can use that in the launch file. So launch files are used to launch multiple nodes at the same time, to execute multiple nodes at the same time. And with this you can easily do this, and this is the format of the launch file in Python, and this is the node which is coming from this ROS actions, and this node is taking the package name and static transform publisher as an executable, and the arguments it will take as x, y, z, your pitch and roll, and two frame IDs, similarly what we did exactly in the terminal, and that will show you the static transformation between the frames. And that's how you can add many nodes over here with the arguments if they have similar and the static transform publishers. And now let's see how we can write a dynamic publisher where the relation between the world and the child frame changes over time. Let us see how we can add a frame and how we can have a fixed frame broadcaster and a dynamic frame broadcaster. Go to adding a frame in Python, and over here we will be creating a fixed frame broadcaster, so that will broadcast the static transform between two frames. Now go to your terminal, in a workspace go to src. Here we will be creating a package, and the command to create a package is this, and we will be creating a package learning TF2 package. And let's enter. Now we have the package already. Let us open the package from here. Go to your home, go to your ROS2 workspace, src, and you will see ROS2 learning TF2 package over here. So Visual Studio Code will help you to manage your code. And in this we have learning to package, and we have an init file here. We will be creating our static and dynamic broadcasters. So let us just set up a bit. Yeah. Now in this, create a file that is static tf.py. So for the fixed frame broadcaster, and we have to make it executable. So go to this, go to the learning package, and right click properties, in permissions, allow executable. Then only the ROS can execute the file, otherwise it will give an error. And now for the fixed frame, you just have to copy paste this command over here. So what basically it is doing is, it is taking from the geometric message type, it is taking the transform stamped message, so which will be used to give the transformation between the frames. And here this is the transform broadcaster from the TF2 ROS package. So basically we have the main, and here we will initialize a node. We will call the fixed frame broadcaster, which is over here class, and this will be spinning the node. And in this we have created a TF broadcaster using the broadcaster over here, and with this we will be calling this function, this callback function, every 0.1 second. So the callback function is over here. So what it is doing is, it is making a message of transform stamped, which is over here. So let us see how do we know that what are the parameters of this message. So these are the content of this message, and which we have to fill, and then using the broadcaster we will be sending the transform. How do we know that it has all of these values? Open the terminal, and then ROS2 interface, go for show geometric messages and transform stamp. When you click over here, you can see the information that the message has over here. So it has the header, and over here we have the frame ID, and we have the translation along X, Y, Z, and the orientation, the rotation as well. So here we can see we have the child frame, we have the parent frame, we have the timestamp, and so on. So those things we have to fill, which is already filled over here, and we will not be doing anything over there. And now let's see how we can modify this. So this is the node name over here we have, and this is the time it is taking, current time. And let's make the first frame, the parent frame, as the world frame, and next we have a child 1 frame over here. So we have two frames, that is world and child 1, and this node, when we run this code, it will give the offset of y between these two frames. So now the relation of these two frames will not change, it will be along y, it will be 2 units. And now let's make a launch file over here. You can go through understanding of this code over here, and now let's make a launch file over here. So in this, create a folder of launch. That's how you organize the files, and put all of the launch files in this. Open a new file over here. Let's see, static dot launch dot py. Great, and then copy the content of this over here. Let me just simplify this. We will not be doing anything with this over here. Remove the demo name as well. Now we have to give the package name and the executable name and the name that we want to give. So now we have learning. Our package name is learning TF2 package, and our executable will be in the, let's go to dot set a file. Here we have to give an entry point over here, which you can see we have already over here, which we have to give, and in the console we will give the name over here of the executable. So a good practice is to give the same name as you have given for your static tf.py file. So we will be give static tf, and then from learning tf2 package we have the same file over here, static, and then it will call the main function over here. So now this is the executable we have, which you have to copy, and in the launch file from this package, this is the executable name. Let's give the same name over here of this package. One last thing we have to do before we build the package, and that is go to your setup file. Here I have the commented lines, but you should add those lines over here. Import OS and globe, and over here we will be adding this line that will find the package, and it will find all the launch files can be executable from this. And now we are done. We have set up everything. Now let us go and build our package and source it, and then launch the file. Go to your ROS workspace and then type build to build your package, to build your workspace. Now we have this. Now source your workspace, install setup.bash. Now we have source everything. Now let's launch our launch file, ROS2 launch. Package name is learning tf package, and the launch file is static static.launch.py. So when you launch this, now this file will execute the static tf.py file over here, and that will publish the fixed transformation from world to the child frame. And to see that, let us go over here and type RViz2 and then enter. Here go to add, scroll down, add tf over here, and then change your fixed frame. We don't have the map frame, so we have only world and child one. So go and shift to the world, and here you can see we have along y 2 units over here. So that's what the static transformation is doing. And now let us add one more node, that is dynamic. So this relation is not changing. Let us add one more node over here related to one frame with respect to the child one frame, and that will be rotating around this. Let's do that. So let us stop RViz, let us stop this, and to do that, scroll down. Here you can see writing a dynamic frame broadcaster, and for that let us create one more node over here. Static is the static, and rename this to dynamic tf.py over here, and remove this content and add the content from over here, dynamic frame. And in this we will make certain modifications. So the parent will be the child 1, and parent will be child 1, and the child of the child 1 will be child 2 over here. And now we will remove this over here to have shorter, and over here we will use instead of taking this, we will use time to get in seconds, just to make the code more simple. Import time, and we will not be using this over here. So now we have everything set up. So we have the child frame, and we have the relation of child 2 with respect to child 1, and the relation will be changing based on the sine and cos functions of time over here. This is a basic algebra. And then go to your setup.py file. I have this file, so you should add this line to your setup.py so that you have this dynamic tf as an executable. Go to the launch file and add this node over here. So from this package, this executable, this is the name that you're providing. And now you have to source, and now you should build your workspace and then source it to have the changes updated over here. And now let us again launch the same file, that is static launch.py file. Now it has two nodes, that is static t1 and dynamic node. And then let us launch RViz over here and add the tf over here, and in that show names so as to know how they are communicating. And now we have the world frame over here. So now you can see there is a world frame over here, and this is a child frame. This has the static broadcaster, and they are fixed, and the relation between child 1 and child 2 is by dynamic frame broadcaster. So that is broadcasting the relation between them dynamically as they are changing over time. So that's how you can create static and dynamic publishers, broadcasters. And in the next video we will see how we can use RViz for better visualization of the data using different shapes, and how we can visualize multiple shapes and lines, curves, and so on. And if you like the content of the video, do like, subscribe the channel, and share the videos through over the ROS community. And we will see you in the next video.